Hey, so we're going to go to 3.5. These are notes limits at infinity, and we can think of these as checking for same thing as horizontal asymptotes. So end behavior of graphs if it's limits at infinity. So one way that we can determine horizontal asymptotes or limits at infinity is we can compare degrees between numerator and denominator. So if we have a function p of x over q of x, then we compare between degrees. If denominator is greater than numerator, then we know that there is a horizontal asymptote at y equals 0. Okay? If the denominator degree is equal to the numerator degree, then we know there's a horizontal asymptote at a over b, or we just take the leading coefficients of the two degrees. If the numerator is greater than the denominator degree, then we don't have any horizontal asymptote, and so our limit is at infinity is either going to be positive or negative infinity. Okay, so this is one method, comparing degrees between numerator and denominator. The other method is we can divide each term by the variable with the highest degree. So for example 1, if we want to find the limit as x approaches infinity, we just take each term. Well, we determine which degree is the highest. So in this case, the variable with the highest degree is x cubed. So we just divide every term by x cubed, just like what we see here. And then we just look to see what the limit is for each of these fractions. So here, x squared over x cubed is increasing at a lot faster rate than x squared. So we know that eventually this fraction will just get closer and closer to 0 because that denominator is increasing at a faster rate. Here, constant over a variable, we know that's going to go to 0. Variable over degree with a variable with higher degree, that's also going to go to 0. And here we have x cubed over x cubed. They cancel out, leaving us with 4. So we have 0 plus 0 over 4 minus 0, which is 0 over 4. So then our limit is simply going to be 0. Second example here. Again, we can find a limit as x approaches infinity. Here, the degree in the numerator. So if we divide every term by x cubed, we're going to see that we get 2, we get 0 here. Degree is higher than the denominator. That's going to go to 0. This will go to 0 as well. So 2 plus 0 over 0. We know this is going to go to positive infinity because this numerator is going to be a higher value than the denominator. Okay. Example 3. Here we have degrees are the same, so if we divide every variable by x cubed, we're going to get 4 minus 0 over 5 minus 0 plus 0, which is 4/5. And so therefore, again, just like before, if we see that the degree between numerator and denominator are the same, we can simply identify the leading coefficients of both of these of both numerator and denominator expressions. Hey, horizontal asymptote, again, is a description of end behavior, not a boundary that the graph cannot cross. So a function can never cross a vertical asymptote. That's a true statement, but it might cross a graph with a horizontal asymptote. So for instance, we could have a graph that looks like this, that looked like this. So here we have vertical asymptotes at, let's say, -2 and +1, and horizontal asymptote at x equals 1. However, this middle branch could have a graph that looks like this. So there is a horizontal asymptote at x equals 1 because we see as we go towards negative infinity, the graph will level out and never cross that boundary. Same thing. As we approach positive infinity, this graph will level out and never cross the horizontal asymptote. However, it's possible that somewhere in between, we may have a branch that crosses this horizontal asymptote. So the asymptote doesn't mean that you can't cross it. It just means that if we follow the graph towards positive or negative infinity, that's when the graph is not going to cross the asymptote. Okay, let's look at some examples here. Finding horizontal asymptote with radicals in the denominator. So this is a different case here. When you have radicals and we're approaching positive or negative infinity, we may have more than one horizontal asymptote. So for instance, the graph of this function will look something like this. So if you look at this graph here, as we approach negative infinity, the graph is going to approach a positive y value, a limit of a positive y value. And as we approach negative infinity, we see that the y value is going to level out at a negative value. So we see that there are two horizontal asymptotes depending on where you're going with the graph. So we need to be able to determine this algebraically without looking at the graph. So whenever you see a problem like this, we're going to have to test both positive and negative infinity, evaluate them separately, and then come to the conclusion what the horizontal asymptotes are. Okay, so the way that we do this, first we're going to find the positive infinity one. Okay, so the way we approach this problem, we're going to divide each term by the variable with the degree of the highest order, just like before. But now, if you look at this expression, the variable with the highest degree may look like it's x squared. So there's an x squared here, but this x squared is sitting under the square root. So that's going to reduce to be x. So that means the variable of the highest degree or highest order is going to be x to the first power. So we divide every term by x. However, once we're under the square root, we're going to adjust it by putting x squared, okay, because we're sitting under the square root now. So now let's evaluate. Negative 2x over x is negative 2. 6 over x will go to 0. 5x squared over x squared becomes 5. 1 over x squared goes to 0. And now we just look at what's left over. Negative 2 over root 5. So that means as we approach positive infinity, as the graph goes to the right, the y value is going to level out at negative 2 over root 5. And that describes this portion of the graph right here. Okay. The second is limit as x approaches negative infinity. So that's the other condition we have to test for. So again, we're going to divide every term by the variable of the highest order. The only thing we have to make an adjustment for is because we're approaching negative infinity, we need to add a negative sign just whenever we're evaluating a limit for negative infinity with these types of problems. So that negative is accounted for out here. And then we look at what we have. We have negative 2x over x is negative 2, plus 0, root negative 5 plus 0. So negative 2 over negative root 5 gives us positive 2 over root 5. So there's a positive. Now this is a very small value, positive value, and that's shown by this portion of the graph here. So there are two horizontal asymptotes for our graph, 2 over root 5, and y is equal to negative 2 over root 5. Okay, last piece of notes, last topic is comparative growth rates. So as we approach positive infinity, we can determine that different families of functions are going to grow at different rates. Not only, but at predictably different rates as x approaches positive infinity. So this is the basic behavior between logs, radicals, polynomials, and exponentials. As we follow the graph of these graphs to the right towards positive infinity, logs is going to grow at the slowest rate, followed by radicals, followed by polynomial, and then finally exponential is going to grow at the fastest rate. So for instance, if you look at this example, y equals natural log of x, this is a log graph. It's increasing, but it's increasing at the slowest rate here. Root x is going to grow at a faster rate. X squared, polynomial, and then finally exponential is going to grow at the fastest rate. It's going to increase the fastest as we go towards infinity. Now, within these families of functions, we may have functions that may initially start off larger than, for instance, possible for a radical to start off increasing faster than the polynomial. However, if we're approaching positive infinity, then eventually, over time, polynomial will catch up. eventually to radical. So in example 5, we have limit as x approaches infinity. We have two different types of functions. We have one family of function being radicals, and the bottom being polynomial. Now, this radical function is going to start off a lot larger than this polynomial. However, the polynomial will eventually catch up. So if we have a radical over a polynomial, eventually polynomial is going to grow at a faster rate than the radical. It's going to overtake this radical portion. So if this eventually gets larger than the numerator, then this fraction will just get smaller and smaller until it reaches 0. So that's what the limit will be for this function. Okay. If we look at example 6, we're approaching infinity. We have two separate families of functions, exponential over a polynomial. Exponential is growing at a faster rate than the polynomial. So that means this will either go to positive or negative infinity depending on what sign we have here. Here we have a negative sign, so that negative is going to attach itself to infinity, so negative infinity.